hello and good morning and welcome. My name is Philip Alviano. I'm the Technical Advisor for Sustainable and Future Built Environments at Master Builders Association of Victoria. You've joined the Better Building Better Homes for the Future webinar this morning, so welcome along to that. I just want to acknowledge too that the sessions we've run, this is part of a bunch of sessions we've run around the state, delivering on the information presented in this webinar, but the sessions have been sponsored by Solar Victoria. They provided the funding for us to deliver these sessions and the webinar this week and the following one next Tuesday morning as well. So look, let's get a start in that sort of sense. Before we get a start, I just want to acknowledge the Wurundjeri people of the Kulin Nation as the traditional custodians of the land where I sit today and where we're delivering this webinar from today. I acknowledge that they've managed and tread softly on the land for the past 60,000 years or so, and acknowledge their leaders, past, present, and future. Okay. So, just the usual things don't really matter here. We'll go for about an hour. We'll finish up just around 9 o'clock or just before 9 o'clock, so we'll give you plenty of time to get out and about. That's the main thing, I guess, this morning. What we're going to cover this morning are the changes to the energy efficiency requirements of the NCC 2022, a look at energy efficient design and sustainable construction. We'll touch on whole of home, and I think that's about as much time as we'll have this morning. Next week, at the next session, we'll look at managing condensation issues and all electric homes. The picture you can see there is one built by one of our members, Nick Wooden, for Wooden Constructions. Built 7 or 8 years ago now. It was an 8-star house designed to maximise use of the sun there, passive solar design, but also you can see very carefully wrapped slab edge insulation there as well. So, well ahead of its time in that sort of sense, and delivering a really nice, comfortable home for their client there. Why is all this happening? Why is all this energy efficiency stuff happening in the construction industry? Well, there's a lot of stuff happening in energy, renewable energy and energy efficiency in this country at the moment. So you can see there, we're not going to go through all of those plans and policies there, but it just gives you an idea of the amount of work going on in the background as well as that. The main one to consider during the construction was this, the Energy Efficiency NCC 2022 and beyond, or the push to zero carbon homes. That is homes that produce more energy, homes and buildings that produce more energy than they actually use. And so that's the main one, looking at improving energy efficiency of houses and buildings. Just to put it in a little bit of context, on the left there of the screen, you can see how the energy efficiency standards have changed over the years. We had 4-star came in 1995. Before then, I think there was just some requirements for ceiling insulation, which was probably only a few more years before that as well. 4-star in 1995. We moved to 5-star in 2006. So 11 years later, pushed an increase in the energy efficiency of homes. Excuse me. And then we moved to 6-star in 2010. So a fairly quick progression there. But we haven't moved we haven't moved above 6-star since about 2010. So it's been nearly 12 years, 14 years now in that sort of sense, now that NCC 2022 has cut in. So, and that came in, as we said, the 1st of May this year, that became part of the National Construction Code requirements. Also, just to put in a little bit of context, I like to compare it, and I guess how our expectations as a community, as consumers, has changed over the years, and I compare it to the old work ute, if you like. In this case, the Toyota Hilux. In 1995, when 4-star came in, it was priced at about $40,000 for your typical work ute. It's now at about $60,000. Given for inflation, that's probably pretty good in that sort of sense. Probably about the same cost. In that time, the engine size is the same, but the output from that engine's tripled. So giving us an idea of how technology is changing and improving things in that sort of sense. We had a 5-speed manual. We've now got 6. We had a radio cassette player with 2 speakers. We've now got digital radio, Bluetooth, and 9 speakers in there. So a work ute with 9 speakers. clearly our sort of expectations of our vehicles are changing, and our comfort levels are changing, if you like. The main one too, and this is where the energy efficiency stuff comes in as well. There were no airbags in 1995 in that vehicle. There are now 7 airbags, plus traction control, plus anti-lock brakes, plus stability control, lane departure warnings, all sorts of beeps that go on as you're driving along to warn you of different bits and pieces. So we've come a long way in terms of safety. If I can liken that in terms of our houses and we live in, we know that people suffer and people get ill and people die when their homes get too cold, but also when their homes overheat as well. So during heat waves, people get ill and people die and hospital admissions go up. So we know it's a really important part of providing good quality, comfortable homes that reduce the sickness in people and deaths, but also reduce hospital admissions and the cost to our health system as well. So it makes a positive impact. And like I said, I guess we can liken it to the sorts of the safety features that cars now feature as well. We had steel wheels. We now got alloys, so we like them a little bit fancier. We didn't have any air conditioning in, or it was optional. We now have climate control as a standard. So again, those comfort levels and expectations have crept up over those years as well. And I guess we expect the same sort of thing from our houses in that sort of sense. Okay, so let's briefly have a look at the changes to the NCC 2022. Most of you should be fairly familiar with these, but we increased from 6 to 7 star. What that would mean, better windows in that sort of sense. So, double glazing, a better quality window frames, also some increase in ceiling and wall insulation values, restrictions on roof colours, excuse me. I'll bring some light back. There we go. And changes to structural floor systems, insulation of the slab, that sort of thing as well. We've brought in a whole of home requirement, and I will talk a little bit about this in more detail in a little while. But the requirement that some of our fixed features and our fixed appliances in that home need to meet a maximum energy budget, if you like. And that's the air conditioning, heating and cooling systems, our hot water systems, the lighting, and any swimming pool and spa pumps that we fit as well. We can interact. We get a maximum energy use budget for all those things. We can interact and switch them around and make some better than others. And we can also offset that with the use of on-site renewables, so solar panels on the roof, if you like. There are also enhanced condensation measures as well. So we've moved to using class 3 or 4 membranes, class 4 membranes in most of Victoria. What does that mean? They're more permeable membranes, if you like. The membranes are now pretty much like a Gore-Tex jacket. So we've moved away from that kind of aluminium foil as well. And sorry, just to mention that too, if you've got any questions, if you drop them in the chat area, we'll see if we can answer them as we go through. The building wrap now is more like a Gore-Tex jacket. So it lets the moisture out as a vapor. So the moisture that's in the air that we can't see, but stops the wind and the rain coming through. So like a Gore-Tex jacket, it lets you sweat out, but it stops you getting wet when it's raining in that sort of sense. So those have changed as well. Again, we'll have a little bit more look at that in detail later on. There are enhanced condensation management provisions for exhaust fans as well. So minimum flow rates for exhaust fans, ducting to the outside. So we're not putting the exhaust into the roof space anymore. We're putting it directly to the outside. We're banning recirculating range hoods. Bathrooms that are not naturally ventilated, so that don't have windows, need exhaust fans with a 10-minute runoff timer. And that's just to keep drying out some of the moisture that's in that bathroom, even once you've finished your shower. So most of the moisture you see in terms of vapor and mist has disappeared from that bathroom, but there's still a lot of water lying around that eventually evaporates and becomes part of the moisture inside the building. So we're trying to get rid of a little bit more of that moisture. There's also additional provision for ventilation for laundries, bathrooms that contain a dryer. So the venting of dryers to outside. If we're sticking a whole bunch of clothes in a dryer that are wet, well, all that water from those clothes is going somewhere. And if it's not going outside, it's going into the house and contributing to condensation issues inside the house. For class 2, so apartments, similar sort of thing. An average of 7 stars across the whole apartment complex, with a minimum of 6 for individual apartments. There are a few new requirements as well in terms of energy efficiencies, there are new requirements for thermal bridging and steel framing. We'll talk a little bit about thermal bridging later on. There are provisions to provide for perhaps the future installation of electric vehicle charging stations. So that means needing to run the wiring in place and have them placed in the car park somewhere, not installing the actual chargers, but running the wiring so it's ready for the chargers to be installed in the future. And that's just that idea that if we run the wiring while we're constructing the building, then it's a lot more to future-proof the building, if you like, for the future. Okay. So where do we start with all of this sort of thing? So if we've put together this pyramid a while ago, which looks at the things at the bottom which make the biggest difference. So where to start, and then we move up the pyramid to things that are really important but make sort of a lesser impact in that sort of sense. So first thing is learning and understanding sustainability, energy efficiency, and indoor air quality. And here you are, you're here today learning about that, which is really important. Passive solar, the next part is getting the design right, and we'll talk about that later on. Getting the design right in the beginning is the most important thing to how that house is going to function as well. Air tightness and sealing up the home, being aware of that, making sure that we don't have drafty homes, that we're building them to a pretty good quality. And the good news is that we are, and we'll talk about that later on. The other way of looking at that too is making sure that we're not building them too tight, so we understand where we're at as a construction process. Insulation is really important. Getting it in, getting the right amount in, making sure it's installed correctly is really, really important. Windows, doors, and double glazing. Excuse me, a single pane piece of glass is pretty much a hole in the wall. It keeps the rain out, but the heat and cold travels straight through it. So, better quality windows make a big difference to comfort levels in those homes. Ventilation. Do we need to add more ventilation to the homes? And we'll talk about that later on. Heating and cooling them. What are the systems we're using? Making sure we're using the most efficient systems we can. Lights is pretty standard now. It wasn't that long ago when we were talking about LEDs. Use LEDs. LEDs are fabulous, except that you've got to get the right ones that make things look nice and the right color and all those sorts of things. Last a long time. Now it's pretty standard in that sort of sense. Energy efficient appliances, and that's the other bits and pieces in the home then that make a big difference. And finally, how can we offset all that with solar in that sort of sense in the home? So, we'll talk about that a little bit later on as well. So, look, just to look at a couple of examples of what we talk about and what's out there, SJD Homes, Simon there, we spoke to Simon originally a couple of years ago now, probably about 7 years or so ago, and he was delivering, all electric homes at that time. 7.3 stars then. Like I said, 5 kilowatts of solar panels on the roof and a battery fitted. It was all electric. He was putting that extra cost of doing that at about $10,000 or so then. I suspect that that's decreased now even further. But these homes actually produce more energy than they use. So a zero carbon home in terms of operational energy as well in that market. But again, a fairly affordable home in that market. We're not talking about really high design homes that are extremely expensive. Another one, again, a fairly builder that puts out a few of these homes every year. Arden Homes, Dean there. I've spoken to Dean for quite a few years now as well. But again, the winner of our Best Sustainable Home Award in 2019. So 5 years ago, they were building these homes. Again, fairly affordable price point, not super expensive, not super custom homes. 8-star, building them to 8 stars, again, with 5 kilowatts of solar on the roof, a battery fitted. Again, all electric homes there as well. And you can see from the design of that home that a really nice home, lots of windows as well. So lots of natural light in those living areas, really nice space to be in. So they weren't compromising in that sort of sense in terms of size of windows and the quality and the livability of that house and the comfort levels of that house. So, again, a really good outcome that people have been building for quite a few years. Okay, so the passive solar design elements, the importance of design in these structures, if you like. So the layout here is pretty much where we start from in that sort of sense. So the sun rises in the east, sets in the west, and travels along the north side of our houses. So it's important to produce, long long skinny blocks that run east-west are perfect in that sort of sense, because we can put the living areas on the north side, and that means that we've got more natural light during the day. We've got warmth during the winter. In the summertime, we keep that sun out, and we'll talk a little bit about how we do that later on. But this is your basic design element. We put the garage on the west side, and that acts as a buffer on those really hot summer days when the sun's setting in the western sky. That just stops that heat from that sun pounding on the side of the house. So it acts like a buffer, if you like, and protects the sun. Protects the house from the sun, excuse me. We put our utilities, our bedrooms pretty much on the south side, and like I said, we protect those sort of east and west facades by using external awnings. So if we design the house correctly, we can let the sun in the wintertime when it's lower in the sky, and we can shade it in the summer. Shade those windows in the summertime and keep that heat from that sun out. And that's really important in that sort of sense. This is where we start. We get that winter sun in, but we keep the sun out in the summertime by carefully designed shading devices on those awnings. They can be permanent or they can be temporary ones, but it's really important that we keep the sun out in the summertime and let it in the wintertime. The important thing is to think about not putting permanent shading on that north side of the house. It's going to make that house dark in the wintertime as well. So, shading that extends out a long way and is going to keep the sun off those windows all year round. That'll produce dark areas that people won't like, but also it'll won't help the house warm up in the wintertime by using the sun. East and west, we have external awnings to keep that sun off those windows when it's low in the sky, and that's really important. East facing, really important that we keep the sun out in the morning, because you can imagine on those hot summer days, the sun coming in on those eastern facing windows will heat up those living areas fairly quickly in that sort of sense. So the other way to do this is to put carports or undercover areas for al frescoes on those east and west sides of the building as well, because again that extends the shading area and keeps the sun off those windows in those areas. So yeah, allowing the sun in on the north, but keeping it out on east and west is really important. So basic, really design features there. Thermal mass is important. It helps to stabilise internal temperatures. So again, in the wintertime, we let the sun in through the windows. We warm up the thermal mass, and at night, as those temperatures fall inside the house, the warmth that's in the thermal mass returns to the air inside the house, and that helps to keep those temperatures up. And again, stabilising those temperatures, reducing those extremes, if you like. In the summertime, we keep the sun off, of course, and because the thermal mass or the slab is connected to the ground, it maintains a fairly constant temperature. And as the air inside the house warms during the day, it's absorbed by the colder slab, and that helps to moderate those temperatures inside the house as well. And you know that on those hot summer days, the dogs flat out on that tiled floor, that helps where it's nice and cool, and helping them to cool their body as well. The other way we can use thermal mass are internal walls. So brick walls, recycled brick walls, reverse brick veneer walls, even earth walls will all act as thermal mass inside a building. Window placement, again, as we've spoken before, pretty simple. We prioritise the north. We try and put as many windows as we can on the north side of the house and those living areas. We shade them during the summer. We let the sun in the wintertime, and then we use less windows on those other parts of the house. So smaller windows, more carefully placed, those sorts of things. The picture you see there is one from Positive Footprints. Jeremy Spencer there. Again, I've spoken to Jeremy for quite a few years. Jeremy's been building 7- and 8-star houses for over 10 years in that sort of sense. And you can see this one in terms of the design. Lots of windows on the north, lots of natural light in those living areas. The high clerestory windows that you can open up, and as the air warms in the building, it rises and escapes out those windows and creates a bit of a cooling draft through that house as well, and helps keep the temperature down. So again, a really nice design, full of natural light, works extremely well in wintertime. We shade it in the summertime, and it works for us then as well. Just a couple of things around windows. Excuse me. Just a couple of things around windows and a couple of terms that you'll hear. First one is that solar heat gain coefficient, and that's just about the amount of energy that's let into the house through the windows from the sun. So commonly treated or low-E glass has a solar heat gain coefficient of about 0.5 or lower. It's higher, yeah. So we want that to be higher on the north or lower and lower on the west. So the higher the solar heat gain coefficient, the more heat from the sun it lets in. That's really important on the north side, but again, on the east and west, we want it to be lower. And we can use treatments. We can use low E glass. We can tint the windows. All of that has an impact on the light inside the building. So, you know, it's a compromise, if you like, but it's certainly ways of doing that and thinking about, again, getting that sun in the summertime, in the wintertime, keeping it out in the summertime, and protecting those east and west facades as well. So that, yeah, again, solar heat gain coefficient, about the heat that's let into the house, or the warmth that's let into the house from the sun. The U value is about conduction, if you like. So that's about the heat conduction through the glass, if you like. So like the idea that we get a steel beam, we stick one end, we hold it in our hand, we stick the other end in the fire. The heat and the cold, the heat travels through the steel beam and burns our hand. And this is what we're talking about, conduction. It's the amount of heat loss that travels through the glass. So if it's cold outside, it's about that cold air traveling through the glass and coming to the inside. So in other words, so the U value, the lower the better. So the ability to stop that transfer of heat and cold through the glass is really important. Okay. So again, sorry, U value is of course aided by double glazed glass, which has that air gap inside that slows down conduction, but also treatment of windows as well. So low E glass treatments and those sorts of things also help with that as well. Sorry, I'm just checking. What's that? Thermal bridges. Thermal bridges are important as well, considerations. As I said, there are now provisions for that for apartment buildings and also commercial buildings, but it's important to talk about them in the houses. The pictures here are an example of thermal bridges, and the idea here is that those steel beams there that are covering a small veranda there on the outside of that building, there'll be double glazed doors under that frame. The steel frame is connected internally to the building and holding that section of building up. Above that, we've got that timber framed area. There'll be insulation in that, of course. There'll be some nice double glazed doors there, probably keeping the heat and cold out. But what we've got is a direct transfer of heat and cold from outside the building to the inside frame of that building through that undercover area, if you like. So you can imagine when it's 1 degree outside, that piece of steel there on the outside is going to be 1 degrees, and that temperature is going to travel through that steel into that internal frame beam there, past the insulation layer, past the double doors, and contributing to a feeling of cold inside that house. So sort of bypassing all the other parts that we put in to reduce the temperature, to reduce the fluctuations of temperature inside that house. So that has the impact of, as I said, on temperature inside by the heat and cold traveling through that. But also what it does is produces a little cold area behind the plaster cover on the inside of the wall, which can contribute to condensation forming on that steel beam. So condensation inside the house is moisture in the air. As the air inside the house is warmer, it holds more moisture. And what happens is when it hits a cold point, the air condenses and it forms a liquid. And that might be happening behind the plasterboard. It might be contributing to mold. But also what it does is it makes a sort of a cold spot in the house as well. And it sort of what happens after a period of time is dust sticks to it. And we get what we call ghosting forming. So if you look at that wall, you can kind of see where the thermal bridging is occurring, because you can see where the dust has stuck to it over the years and that sort of sense as well. Okay, so window frames are important thermal bridges as well. And this little example that I found at a home show a couple of years ago now shows you the importance of window frames with thermal breaks and just how much heat and cold travels through those frames. So the example in the centre picture is there's an ice bath in the bottom there, and we've got 2 examples of window frames there. The one on the right has no thermal bridge, and the one on the left has a thermal bridge in it. You can see that kind of dark strip through it as well. So what we're simulating is, the back part of that frame, so the part that's connected to to the wall there is in the ice bath, and the front part, which is the internal, which is simulating the internal part of the window frame, it sits above the ice bath. So it's not connected to the ice bath other than through the connection at the back of that frame there, if you like. So the one on the right shows that the ice bath temperature is at about 4 degrees, and that frame on the right there is in contact with that ice bath, and then it makes direct contact with the part of the frame that will be inside the house, and you can see that the temperature on that frame is 7 degrees. So the cold from the ice bath or the outside of the building is travelling straight through that frame to the internal part of the frame there, and again, it's making it extremely cold and providing a spot not just for temperature to come into the house, but also for condensation to occur. The one on the left is connected to the ice bath as well at the back, so the external part of the window frame, but the thermal bridge is preventing the temperature travelling through that frame to the internal part of the frame, which would be inside the house. So while the ice bath is at 4 degrees, the temperature of that frame that's inside the house is at 21 degrees. So it was about the temperature inside the building, if you like. So again, showing the importance of a thermal break in those frames as well, and the amount of heat and cold that can travel through window frames. Now, we generally don't think of them as much because they're only a small part of the window, but makes a significant difference to the performance of the window. And we can see that here where we have the U values of different types of windows. So the one on the top there, the top circle around the 5.4. So the U value of the single pane piece of glass with a timber frame is 5.4. If we go to the trouble of double glazing that window, but we fit an aluminium not thermally broken frame, you can see that the U value is 4.8. And not a big difference. If we convert that to the R value there, it's about 0.1 of an R difference between those two frames there, two windows there, if you like. So it shows you the importance of that idea that, look, you've gone to the trouble of installing a double glazed piece of glass and the expense of that, but because you're still using an unbroken aluminium frame, it makes almost no difference to the performance of the house in that sort of sense. So in terms of calculating your star rating, it's not giving you very many points at all in that area. Now, we know aluminium frames are great, right? They last a long time. We don't have to maintain them, so fantastic. But we've got to work a way around that. So we either have them thermally broken, we can get composite aluminium frames, so aluminium on the outside where they protected from the elements, and timber on the inside. We can use other types of frames, UPVC, or all timber frames as well. So again, the importance of the window frame in terms of the ultimate performance of that house is really useful as well. So, thermal break. So an idea of the thermal break in a window frame. The picture on the right there, it's pretty much that strip of rubber or plastic that separates the internal aluminium part of that frame from the external part, and again, just stopping that temperature traveling through that from the outside to the inside. On other sources, structural beams, balconies, those sorts of things, it's basically a piece of rubber again or other material between the two pieces of steel that reduces the thermal bridging between the two pieces, the internal part of the steel and the external part of the frame there as well, and just stopping again that temperature traveling along that steel beam. We will get some thermal bridging through those bolts there, but not a huge amount. And there are other ways of eliminating that entirely as well. Okay, let's just check. Yep, what have I done? Back to that. Okay. So let's move on to whole of home. Whole of home is that idea that we now need to sort of account for the energy budget of the fixed appliances in that house. So we need to get a 7-star rating, plus we need to comply with the whole of home requirement. And that, again, that's covering things like our heating and cooling appliances, our pool pumps, any pool pumps or spa pumps, hot water systems, lighting, and then we could offset that with on-site energy generation as well. So the score it's given at the moment is 60 out of 100. So we need to be better than that in that sort of sense. And that just relates to a home that scores 100 is a net zero home. So the energy going into that home the home is producing more energy than it's using in that sort of sense. So it must be above 60 using a NatHERS rating. We'll have a little bit of a look on what that all means and what the NatHERS rating means, and reacquaint ourselves with how that works. There's a short video, so just give me a minute and I'll load this up. So let's go sharing here, and let's go to this one. Go to that. There we go.
Good design is key to building modern, energy-efficient homes that are cheaper to run and more comfortable to live in. The nationwide House Energy Rating Scheme, or NatHERS, has been guiding good home design since 1993. NatHERS is the most popular way of meeting minimum requirements for new builds in the National Construction Code. More efficient homes help reduce energy use and improve the reliability of the energy grid for all Australians, helping us on our path to net zero by 2050. NatHERS assessments provide a star rating out of 10 based on hundreds of factors, such as the home's construction, local climate, and orientation on the block. CSIRO Science drives software that estimates the amount of energy needed for heating and cooling. Just like the ratings for fridges and TVs, the higher the star rating, the lower your bills. NatHERS can improve the energy efficiency of your home during the design phase. Simple changes can significantly increase a home energy rating, improving comfort and saving money on bills. Appropriate shading on the western side of a home can be added, or the house can be rotated to face north to capture winter sun. More insulation could be used, and double-glazed windows could be added. A home energy assessment also helps you make decisions on energy-efficient appliances suited to your family and local climate. A NatHERS certificate shows an additional energy performance score out of 100. This includes hot water, heating and cooling, lighting, cooking and plug-in appliances, as well as pool and spa equipment. The rating considers energy used for heating and cooling and appliances minus energy generated from solar panels, building a useful snapshot of energy costs as well as greenhouse gas emissions. The updates to NatHERS are also providing the framework for banks to offer green home loans and help drive demand within industry for the skills needed to focus on energy efficiency. Learn how NatHERS is guiding the design of the next generation of Australian homes at nathers.gov.au. Explore ways to improve energy efficiency at yourhome.gov.au.
Look, I'll just stop it there for a sec. Just a couple of points there. That Your Home website, really useful for getting more information in terms of what I've been speaking about, getting that design right, all the thermal mass stuff, the thermal bridging sort of ideas as well. Lots of really good, useful, easy to understand information there on the yourhome.gov.au. It's a great spot to point your clients to as well, in terms of them coming to you and saying, oh, look, I want to do something like that, but I'm not really sure where I start or what I should do. That's probably a good spot to point them to in that sort of sense. Okay, let's go back to our presentation. There. Okay. So look, let's. What I want to do is, there's a calculator on the ABCB website that looks at that whole of home calculation. It gives a bit of an indication of how it all kind of works. So I'm just going to open that up, and I can have a bit of a play with that and work our way through it to give you a bit of an explanation around that. So let me just check something. I've still got this. Let's have a look, and we are. Okay, so if we have a look at the calculator and we start at that sort of top section there, you can see, basically your project name, where you are, the climate zone, which is going to be important in terms of energy use, the size of the building, again, which is important in terms of energy use, the classification, in this case a class 1 or a house. You can see on the right there, it tells you how much you're allowed to have for that sort of size building and climate zone, and then it tells you whether you've met that or not. At the moment, we're not meeting it. We've got a pool in, so let's get rid of that pool for the moment. And you can see even without the pool, we're still not meeting it. If using a heat pump, specify the rating type here. In this case, it's the GEMS rating. So that's the star rating that is on the stickers of air conditioners and dishwashers and all those sorts of things as well. In this case, we're using ducted heat pump system, so we can play with this a little bit. So let's see what options we got here. We can have ducted gas, ducted heat pump, or non-ducted heat pump. So let's at the moment, let's try ducted gas if you like for heating. And we're using let's use some splits, non-ducted heat pumps to cool. Okay, reselect. I think it's got to do with the star rating here. Yeah. Okay, so you can see here that we've got a heat pump to heat our hot water. In this case, so electricity to heat our hot water. And you can see here that with ducted gas systems, we've got splits to cool the house, and a heat pump, electric hot water to heat the house. We're not meeting the requirement without solar panels. Okay. Let's put in an instantaneous gas system, if you like, as well. Let's stick that in. You can see, again, we're well over the allowance for that we're required for the energy budget to heat and cool the house, as well as provide our hot water using gas appliances. Let's see what happens if we stick some solar panels on there to offset that. About 6 kilowatts seems to be a kind of standard at the moment. If we do that, we meet the energy budget. And a kind of important consideration here. So let's try it a different way as well. So let's get rid of the solar systems. Again, you'll see we're not meeting the systems. Let's put in, for cooling, let's put in ducted heat pump for heating of a fairly, efficient standard. Ducted heat pump for cooling. Again, so a whole of home heating and cooling systems. We've still got gas instantaneous. It's not, we need to pick the number here. So let's go here. Okay. So you can see we've got some pretty good ducted heat pump systems, so whole of house heating and cooling. We've got gas instantaneous still. Let's go back to a heat pump off peak. And you can see we're still not meeting the requirement without having to fit solar panels, even though we've got some pretty good efficient appliances. And that's what we're starting to find as builders are starting to use this. It's quite difficult to build a new home with ducted heat pump systems, a whole of house heating and cooling without adding solar panels on them. Let's go to splits. So if we go to splits, so non-ducted heat pump, non-ducted heat pump. Okay. So you can see now if we use non-ducted heat pumps, so split systems to heat and cool the house, heat pump, really good heat pump, hot water system, we meet the requirement without having to fit solar panels. That's an important thing to think about there in that sort of sense in terms of what your clients might want and what you might delivering. This whole of home calculation seems to be pushing us towards electric appliances and seems to be pushing us to non-ducted heat pumps or split systems rather than ducted. A little bit more efficient than ducted because we're not losing heat and cool by shipping it around the house, moving it through pipes as well. The heat and cold's generated directly there and straight into the house. So again, the most efficient way to do that. But you see that if we don't do this, then we'd find it difficult to meet the requirement. So let's go back to ducted. Again, lots of people like their whole of house heating and cooling systems. Let's go back to ducted here. And you can see we don't meet the requirement, so we've got to stick some solar panels on. Let's say 5 kilowatts, and we meet the requirement. So again, most of the time, unless we're using really efficient splits, we're going to have to put some solar panels on a new house as well. If we stick a pool on it, let's go to the split systems again. So let's just go back to splits again. Non-ducted heat pump. Non-ducted heat pump. Let's get rid of the solar. you can see, okay, at the moment we're meeting the requirement. Again, you know, the most efficient way of heating and cooling that house and heating our hot water. We stick a pool in, 30,000 litre pool, all of a sudden we don't meet the requirement. So again, let's stick some solar on the roof, and we do. So again, the other lesson is that if you're putting a pool or a spa pump in, then you're going to have to put some solar on the roof as well. There are rebates available for solar installations for new homes as well. We'll go through that next week as well. So just a little bit of a play with the old calculation of the whole of house system. So again, just trying to get you a little bit familiar with that as well. All right, let's go back to the presentation. There. Share. Okay. The other thing to think about and remember too, and as we said, we'll send you out a copy of the presentation as well, but for heat pumps, they don't have a star rating at the moment. So the energy radar, or in your calculations, you'll be using the small scale technology certificates. So these are the sort of allowances that allow for the efficiency of the product and that sort of sense. It measures the efficiency of the product, but a different way to the the star rating system as well. There's a calculator to do that, but you know, again, your energy rater should be able to do that based on the brand and the model of appliance as well. So just that's an important thing to remember as well. Look, as we move away from that, some of the trends we're starting to see in residential housing is that idea that houses interact with their environment as well. We know that, you know, we know that in the past, as wind blows over the house, that picture on the bottom creates an area of low pressure, like the wind blowing over an aeroplane wing. Creates an area of low pressure and creates lift or sucks that roof up into the sky. We know that, you know, areas that have really strong winds, cyclones, we need to really tie down those roofs. But what's also happening is the wind blowing on one side is creating a positive pressure on that side, and on the other side, which creates a negative pressure on the other side. And so we're getting wind pushing air into the building, and on the other side, it's sucking the air out. And this is creating drafts inside building. So we know that air tightness is really important. And we've been starting to measure that over the last few years in Australia. And the idea is that they stick a dirty great fan on that front door. we suck air out, or we blow air in and out. There is a standard procedure for doing that. It simulates a wind blowing on that house of about 30 kilometres an hour, so about a fairly stiff breeze, enough to move the small sort of twigs on a tree, if you like. So not strong, but a fairly stiff breeze, if you like. And we can measure the air tightness of the houses. Now, the NCC says that our air tightness should be less than 10 air changes per hour, per cubic metre at 50 pascals of air pressure. But we don't really measure that at the moment. Probably a good idea to do that in a house. Now, compared to the rest of the world, France is at about 5.5 air changes per hour. The US for climate zones similar to us is at 3. Germany and Belgium are at 3 as well. And passive houses, 0.6. So pretty much really airtight houses. We'll talk about passive house a bit later on. So how we compare with the rest of the world is sort of, debatable at the moment. Like I said, there is an air change requirement in the building code, but we don't actually test for it to make sure that we're actually achieving that. And just to give you an example of what the blower door test looks like and what it does, I've got a little video here. Let me just, sorry, I shouldn't have done that. Let me go share. Go here, share that. Okay, again. But yeah, a little smoke machine there. The doors, the fan's sucking out air out of that house, and you can see there's quite a big air gap behind the oven here, behind the tree there. Yeah. An internal sliding door there, and the amount of draft coming through the internal slider there as well. So really important that we build these things. I'll just play that again. Really important that we build these things properly, that we seal the gaps. The other important thing is that, spiders, insects come in through those gaps, dust and dirt and
it's a poltergeist shield
through the gaps. So all that's really important in terms of, again, maintaining a fairly healthy house as well. So yeah, quite a bit of draft there coming through internal cavity slider. There are ways of building these things. So let's go back to the presentation. There are ways of building these things to make sure you don't get that issue. Presentation gone. There it is. But yeah, again, the importance of stopping the drafts and measuring the amount of drafts. Fairly new home being built there as well. The good thing is that we're actually getting better at building our houses. We're building more and more airtight houses now as well. The comparison, there was a study released by the CSIRO very recently, about a month or so ago, that looked at the airtightness of houses. It compared it to a similar study they did in 2015. Now, in 2015, the airtightness, the range they measured ranged between 6 and 27 air changes per hour from the houses they tested. Now, 27 air changes per hour is kind of like having the front and back door open all year round. Pretty much all your heat and cold's going straight out of that house. The houses measured were all fairly new, within about 10 years old in that sort of sense as well. The average they found was 15, which is still, fairly high in that sort of sense. And again, higher than what we're asking for out of the NCC now. The good news is that we're actually getting better. We measured this fairly recently, as I said, and we found that the average air tightness rate for houses was 7.6. Pretty good. Under the NCC requirement, 7.6 is pretty good. Once we get around, 5, 6, we're starting to get pretty good air tightness levels there without having to add ventilation into a house. The minimum was 1.63. This is important too, because I kind of say to people, that's probably good to have a blower door test done every once in a while on your house to see where you're at in terms of building. Because something that has an air change rate of 1.63 is relying on people opening those windows and doors fairly constantly or providing a ventilation system for those homes as well. And we'll talk a little bit about ventilation systems later on. The maximum was 15. So again, not great, but, compared to 10 years ago or so, not a bad sort of result. For apartments, they found the average was 5.8, so a little bit tighter. As you'd expect, I guess, using things like tilt concrete panels would, generally make those fairly tight. The minimum was 0.79, and again, this is really important there in the sense of we're now starting to impact on indoor air quality levels, and we need to make sure that these spaces are properly ventilated as well. And the maximum was still 15. So, not a great outcome there compared to the averages on the apartments. So, again, these are important. The maximum air tightness rates are really important. The averages, but also the minimum rates measured are really important there because they do have an impact on indoor air quality. The other thing we're seeing, and I'll just briefly talk about it, zero carbon housing, which is operational versus embodied energy as well. So up until now, we've been focusing on operational energy, the energy it takes to run the house for about 50 years or so. And we've been focusing on bringing that down. As we're getting tighter and bringing that down now, we're starting to look at, okay, well, how much energy we're actually using to build the house? And that's the embodied energy, if you like. So that dark green spot on the right, that 33% initial embodied energy, and then recurrent embodied energy as well. This is about, what are we using? We're using concrete, we're using steel, we're using bricks, but it's also offset by this recurrent embodied energy, which is the amount of energy it takes to maintain those materials over their life cycle. So we know some things are inherently high in embodied energy. Bricks are high in embodied energy, but they're great. We put them on the wall. We don't have to think about them anymore. They last a long time. People like them. We don't have to maintain them. So we don't spend any more energy painting them, replacing them when they, wear out or those sorts of things as well. So that's really important consideration of embodied energy. The discussion and the answer is not that simple, if you like, as well. So I just wanted to briefly introduce that because we'll start to hear a little bit more of that over the next coming years, if you like. The other idea is passive house, and passive house are super airtight, super energy efficient, don't rely so much on the orientation and passive solar design because they are so airtight and so efficient. They have ventilation systems that provide fresh filtered air into them, but you don't lose the heat and cold. The air that comes into the house travels past the air that's going out. They swap the temperature, the heat or the cold, And so we're not reheating or cooling that air again, but we're getting fresh air into the house. And that's really important to do that there. The picture there is one by our builder, Granted Constructions. I think it was one of our awards winners a few years ago as well. There is a short video on Passive House. Let's have a bit of a look at this. Yeah, go back.
Yeah, okay. Passive House explained in 90 seconds. Does your house have a heater in the basement or maybe a fireplace? Probably also a central air conditioner or maybe a window unit. Did you ever explain in 90 seconds? Does your house have a heater in the basement or maybe a fireplace? Probably also a central air conditioner or maybe a window unit. Did you ever wonder if it was necessary? In 1991, a physicist in Austria, Dr. Feist, built the first passive house. Here's what he did. 1. Proper insulation. It's just like wearing the right winter jacket, it also doesn't need a heater. 2. No air leakages. There should be no holes, small or large, to let hot air out of the house. 3. No thermal bridges. A thermal bridge is like a road for heating energy in which warmth can travel right through your walls. As a matter of fact, most of our houses have thermal highways in our walls where heat can easily travel to the outside. Plus, the house needs proper windows most of the time with triple pane glass. It needs to be oriented properly so the sun can heat it in the winter and shade is provided in the summer. And it uses an HRV, a device that provides the inside with fresh air without letting the heat out. Add all these things up, and it turns out your house doesn't need a heater or air conditioner. So where does the heat come from? A passive house needs 90% less energy, and that can easily be supplied by your body heat, the sun, your appliances, light bulbs, and even your TV. This saves you a lot of money on your heating bill and helps preserve the environment.
Did we make it in 90 seconds?
You bet we did.
So again, that idea is, really tightly airtight build, a ventilation system, really well insulated, really good quality windows. Look, I mentioned Passive House because I am starting to see quite a bit of it. It's quite interesting because we first started speaking about it, probably 7 or 8 years ago now. We thought, yeah, look, it's a great idea, but I'm not sure we'll see much of it in Australia. But we are starting to see quite a bit of it. If you want to learn more about that, there is an Australian Passive House Association that has more information, also has various training courses as well on that. So, worth having a bit of a look at that if you're starting to get that question from clients. But again, a really super efficient way of building in that sort of sense. Okay, how are we going for time? We've probably got a little bit of time to go through the condensation part of the session. Look, condensation in a house, it's produced in a variety of different places. The air we breathe, the clothes drying inside, our cooking, all bathrooms, all those sorts of areas produce moisture and put it into the air as vapor. So we can't see it, but it's in the air as humidity, if you like, in that sort of sense. And when it hits a cold surface, so like that glass in the picture there, it becomes liquid again, condenses and becomes liquid again. And that idea is that liquid on that glass is coming from the moisture in the air, not from the liquid inside the glass. And so we want to think about that in terms of the moisture can pass through the wall and through small openings in plaster walls. And we want to make sure that the air, that moisture is not condensing in the insulation layer or in the wall where it can't dry, where it doesn't dry out, and it might be forming mold or starting to damage what's in those walls as well, our structure. So again, we produced these flyers a couple of years ago now. They are available on our website, but we will send you a copy of them as well that you can put in a handover kit for your clients. Like building an energy efficient house, the best way to destroy an energy efficient house is to let people live in them. The same sort of thing with moisture and condensation. The place to start is to looking at how people are using their house. So they're exercising inside the house. There should be a window open because they're breathing and they're sweating out moisture in the air, so they're pumping moisture into the air. Laundry, the same sort of thing. If they're washing clothes, drying clothes inside, all that weight and that moisture in those clothes is going into the air. Showers, again, it's not just the moisture and the vapor we see when we're having a shower, but it's also all the water lying around the shower and where that's going. Are they closing the door? Are they using the fan? Is the fan working efficiently? Is there enough gap under the door to make sure that fan can extract all that moisture out? Does the fan run on afterwards? All those things, and also cooking as well. So that big pot of pasta boiling on the stove, all that moisture is going into the air if we're not using the range hood properly. So all those things have an impact on indoor moisture, has an impact on our health. It can cause mold where we can see it on the walls. It may be occurring inside the wall, maybe occurring under carpets, and maybe occurring behind cupboards, but also maybe occurring in the structures. That photo there, bottom left, you can see that that the moisture in the wall is damaging the building structure itself. So really important that we understand this and we control this. There's a couple of resources out there. One is the ABCB condensation handbook. The other one is the Tasmanian guide. The Tasmanian guide is great because it has lots of pictures in there of what your wall structure should look like to help present issues of condensation. So in this case, it's looking at that wall, the idea of an eave vent. So the eave vent and a clear path for the airflow to flow between the building wrap and the external facade, or the tin roof in this case, in that sort of sense. So what that does is as the air warms up in that roof space, it travels up the roof and out the top, and it draws fresh air in from under that eave vent along there, and it helps to dry that space, helps to dry any moisture sitting on the building wrap there as well. We've got to make sure that there's a cap at the top. The ridge cap is open enough to allow the ventilation through, and that there's no battens or anything like that stopping that airflow going past and going through that gap. So really important there as well. And again, that's from the Tasmanian guide. There's all sorts of products out there that help to ensure that we've got those air spaces there as well. Vented battens, ridge vents, fascia vents, all those sorts of things as well out there in the market now to make sure we keep those spaces open. Wall spaces, similar sort of idea, and again from the Tasmanian guide, that we separate the facade from the building wrap. We make sure there's a clear air gap there, and that allows, again, as that air heats up and in that wall space and rises, it draws fresh air through and it dries that building wrap and it draws the moisture out of the wall. So really important that we're spacing the facade off the building wrap. We're making sure there's a gap there, if you like. And again, lots of information in that Tasmanian guide around that sort of thing as well. For bathrooms, it's about installing, run-on fans that will run for a certain period of time, even once people have switched them off, just to make sure that they're taking all that moisture out of that area. And as the water in the bathroom itself evaporates after people have used it, there are fans with humidity sensors that come on automatically as well. So they'll come on and off as required once the moisture in the air reaches a certain level. They're a continuous fan, so they'll run slowly and just keep drawing air through that space, and again, just drying that space out continually. There are also simple heat recovery ventilation systems. So these aren't Passive House accredited ones, but they're simpler. They use standard ductwork that we use for heating and cooling, so can be installed by more people. And the idea of these is that they pump fresh air into bedrooms and living areas, and they take it out of the wet areas, the kitchen area. And so they're pumping air through the houses each time around the house. Again, heat recovery, so you're not losing your heat and cold, but they're pumping fresh air, filtered air through them as well. So they're worth investigating perhaps with clients as well. Okay, I think, in terms of the ventilation as well, there are increased requirements through the NCC for building membranes. We now have to have class 3 or 4 membranes. And as I said, pretty much anything along the Great Dividing Range and South of Dividing Range are class 4 membranes. And that's about just how permeable they are in that sort of sense. So, yeah, the picture shows it fairly well there. That northeast corner, the warmer sort of dry area, class 3 are okay, but definitely class 4 in those southern areas there as well. Again, just making sure that the right sort of membrane is rolling up to your site when you're installing it. Checking the labels on those membranes as well. There are some Australian standards related to that. One is about the type of material and the membrane and the permeability. The other one is about how to install it, make sure it's installed correctly. So pretty sort of standard there. Okay, look, I'm going to leave it there. We've run out of time this morning. Thank you very much for coming along. Next week, we'll be touching on, as I said, all electric houses will be finalising and finishing up on some of these things. So I look forward to seeing you again next week, and hopefully some more people as well coming along to that next week.